Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series. This time, the topic is another interesting topic, the basics of a power transmission line. And my good name is John Kweko Amoto, and I've been an electrical engineer for the past 31 years, and I'm based in the United States of America. Now, let's talk about, the next slide is an outline of my presentation. And the first thing we'll talk about is basically how transmission lines are classified, right? So transmission lines are classified based on voltage and the length of the transmission line. So these two go together, right? It's voltage, level, plus the length of the transmission line, right? That is what is utilized to be able to classify different or obtain different classifications of transmission line. Then we'll move on to talk about the different components of a transmission line, and the first thing we'll talk about is the different towers that we have. We have a typical example is suspension towers, tension towers, and we'll talk about insulator supports, the different types of insulator supports that supports these conductors, when they are basically being run over their towers. Next is the shield wires, right? Okay, so that is a ground wire that basically goes on top of the tower structure. Basically, that is the one that protects the phase conductors from direct lightning strike. Then next is surge arresters. Yeah, at different locations as part of the transmission line length, different surge arresters are installed based on insulation coordination studies and basically its goal is to protect the phase conductors from lightning strike that basically can result in overvoltage condition or any other fault condition that can result in an overvoltage condition. Next is the grounding. As you know that a transmission line spans different several hundreds of kilometers, thousands of kilometers, right? Okay, so per design, basically grounding points are determined at various lengths of the transmission line to allow basically ground fault current basically to be discharged into the ground grid. Next is other hardwares, right? And typical example, it's dampers and spacers. Dampers are the ones that basically dumps, the vibrations from the conductors to prevent a phenomenon called wind clashing. Where basically you have a wind, excessive wind force that basically excites the conductor and basically can allow two conductors to clash into each other, right? So you have dampers that are basically installed at various positions to dump out vibrations that can occur when the conductor is excited based on an excessive wind velocity. Another hardware that we'll talk about are spacers, right? Okay, so sometimes based on the amount of current, if a phase current is so high, then bundled conductors are put together per phase. So a typical example is you can have 4 conductors that are bundled together in one phase, right? Okay, so if you have 4 conductors that are in one phase, you need something that is going to keep it rigid in space, right? From preventing each conductor from clashing into each other due to the wind. Okay, so now let's talk about classification of transmission line. Okay, so as you know, transmission line basically allows the transmission of electrical power over several hundreds, thousands of kilometers, right, from the sending end to the receiving end, right? Okay, so you have the sending end, you have the receiving end, and this is several hundreds of miles or thousands of kilometers, right? spans of towers across the entire length of the transmission line. Okay, so uh, transmission lines are built based on mechanical strength, right? Okay, so the transmission towers should be able to support these conductors that are basically installed in space, right? Okay, and basically it has insulator disc, also, you know, other hardware that is supposed to support, right? Okay, so during the design of these transmission lines and towers, right, mechanical strength is taking a deep look at so that basically these lines wouldn't sag, or, you know, due to excessive wind, excessive rain, and excessive ice, basically they wouldn't sag as it is in service, right? Okay, because excessive ice fall on or snow basically can, the weight of the ice and the snow can cause these phase conductors to sag, right? And if it sags, basically, then it can create other problems, right? Okay, and as much, and also, you know, if you have excessive rain, right, basically it can cause short circuit in between their phases. And also, you know, if you have excessive wind velocity, right, it can cause something they call conductor galloping or conductor clashing, right? Okay, where one conductor from another phase can clash into the other, basically cause temporary short circuit. Next is the economics, right? Okay, so uh, because for you to transmit electric power across several hundreds of and several thousands of kilometers from the sending end to the receiving end, right? You always think about, you know, which one is the best choice, right? And much cost effective, right? So comparing underground cable with overhead transmission line, basically overhead transmission line becomes more economical over several hundreds of kilometers to several thousands of kilometers, right? Okay, so I've seen, you know, if you go to China, they have about transmission line, you know, to about 4,000 kilometers, right? Okay, so that is when the economics comes into play, right? Okay, and you basically decide to implement an overhead transmission line. But for shorter distances, let's say if you have something like 10 kilometers, 5 kilometers, then basically, you know, it becomes cost effective to utilize an underground cable transmission system, right? Also, you know, the mechanical designs, a lot of robust mechanical design is put into um, conduct transmission line, right, to achieve the required spacing in between conductors. You know, if you have conductors that are bundled in each phase, right, there's a spacing that is required. And also conductors from phase to phase, there's a required clearance that you're supposed to have for these transmission lines. And also the clearance of a phase to ground, right? You know, between the conductor and the ground surface, right? You're supposed to achieve that to prevent arcing and also excessive leakage current through the stray capacitance. Okay, so electrical transmission of power can be achieved, you know, by overhead line or underground transmission line. These are the two means of an underground transmission system. Most often than not, it is through a transmission cable, right? Okay, so transmission line can be classified based on the voltage level, right? Okay, and I explained, you know, in the previous slide, based on a combination of the voltage level and the transmission distance. So these are the two elements, these are the two criteria that forms the basis of the classification of transmission line. Okay, so let's look at a small transmission line, right? Okay, so for a small transmission line, if you have voltages up to 20 kV, and also you have a distance of up to 50 kilometers, right? These two. So a transmission distance of less than 50 kilometers plus voltage level of 20 kilometers, the two together basically forms the basis of achieving a short distance transmission line. Next is medium distance transmission line. Okay, so for medium distance transmission line, if you have a transmission line that has a line-to-line voltage of 20 kV to 100 kV and also transmission distance of 50 to 100 kilometers, then you can classify that transmission line as a medium transmission line. Next, for large transmission line or long distance transmission line, right? If you have voltages, line-to-line voltages of greater than 100 kV and transmission line distances of greater than 150 kV, these two criteria forms the basis of long transmission line, right? So we have three classes of transmission line classification, right? The first one is short distance, and that is based on transmission line length that is less than 50 kilometers plus line voltages of up to 20 kV. Next is medium transmission distance transmission line, right? If you have a line distance, transmission distance of 50 kilometers to 150 kilometers and a line to line voltage of 20 kV to 100 kV, then you can classify it as a medium distance transmission line. And lastly, if you have distances that are greater than 150 kilometers and you have line voltages that are greater than 100 kV, then you can classify that transmission line as long distance transmission line. Now let's take a deep dive into the components of a transmission line, right? Okay, so as you can see over here, this is what they call the phase conductors, right? Okay, so the components of a transmission line consist of tower structures, right? And these are the tower structures, as you can see over here, right? These are the tower structures all the way from the top to the bottom, right? All the way from the top to the bottom. These are the tower structures. Then the cross arm, right? The cross arm is what is shown over here, right here. This is the cross arm. That is the one that is supporting the phase conductors, right? Through suspended insulator. Next is the phase conductors. These are the phase conductors. These ones are the phase conductors. These are the phase conductors, right? So you have a three-phase system here and a three-phase system here. So phase A, B, and C over here. Next is support insulators. So the support insulators are what you see over here, right? These are basically porcelain disc or hardened glass disc, right? That basically are put together, right? Each disc is about 11 kV voltage. Supports can withstand about 11 kV, right? Okay, so based on the operating voltage of the transmission line, then that determines the number of discs that are put together, that are basically joined together to support this conductor. Okay, so next is surge arresters. So surge arresters are installed at various strategic locations based on insulation coordination. And most often than not, at locations where there's an interface between a transmission line and a cable, right? The junction between where you have a transmission line, then basically you have an interface of a cable that is going to go underground. Yes, that break in impedance, basically, most often surge arresters are installed on it. Next is shield wires, right? Okay, so the shield wire, this is an example of a shield wire, right? So that is basically installed on top of the tower, right? And sometimes some people call it earth wire or ground wire. Okay, so earth wire or ground wire. Okay, and what is its function? Its function is to basically protect the phase conductors, phase A, phase B, phase C. If you have a double circuit, phase A, phase B, phase C, sometimes you can have two shield wires on a tower, right? Depending on the number of circuits, right? Okay, so its purpose is to basically protect the phase conductors from direct lightning strike, right? So let's say a direct lightning strike will hit the shield wire and will be connected to ground at the required at vantage points where there are ground wires that basically goes down the tower structure onto the ground grade. Okay, so at various positions, at various spans of the transmission line, there are grounding points, right? And typical impedance for the grounding points for this transmission line towers is about 25 ohms, right? Okay, so if you go to distribution voltage level, you're supposed to have about 15 ohms of ground resistance, and for higher voltages, it's about 25 ohms. So now let's go to other hardwares, right? Okay, so other hardwares, you can have spaces, right? So I indicated that sometimes if you have more than 2 conductors in phase, you can have 2, 3, 4, 5, 6, right? That are bundled together, right? Sometimes the phase current is so high that you want to put conductors in parallel to share the phase current. Then that is when you bundle them together. And if you bundle them together, there's a spacer, that basically holds these conductors in place, because the goal is to prevent the conductors from clashing into each other when you have a gust of wind, and also to maintain the space between those conductors, and also to maintain the space between phase to phase, right? You have a phase A, phase B. The goal is to maintain this clearance, right? And the goal is to maintain the clearance from phase to ground through that straight capacitance has to be maintained, right? So that is when you utilize these spaces. Next is dampers, right? You have dampers, right? An example is of a damper is this, right? Okay, so these dampers are installed at strategic locations, right, throughout the whole entire length of the transmission line. And what is its purpose or its function, right? Okay, so since this transmission line spans for several hundreds, several thousands of kilometers, right? Okay, so if you have weather conditions, extreme weather conditions where you have excessive wind, right? During the design of these transmission towers and transmission lines, right? Feasibility studies is conducted based on the worst case velocity of wind that is going to flow in that area, right? Okay, so dampers are installed on these transmission conductors, right, to damp out the vibration that will occur if any of these phase conductors should be excited by any high velocity wind. The goal is to prevent the wind from basically experiencing a phenomenon called wind galloping or wind clashing, where it can clash into other phase conductors and cause a short circuit. On the other hand, at distribution levels, right, you can have a pole-mounted step-up transformers, right? If you have a distribution levels, you have the cross arm right here. You can have a pole-mounted distribution level transformers that basically can step up the voltage or can step down the voltage. You can also have voltage regulators at the load end, basically to be able to regulate the voltage to the load. You can also have surge arresters, right? You can also have fuses, reclosers, fuses, right? Basically, those can be installed on these poles on the distribution and transmission lines. Next is a typical tower structure classification. Okay, so these towers are designed and installed based on voltage, right? Okay, so up to 69 kV, I'll say that you can have this type of tower structure. They call them tangent type of tower structure. It forms like a triangle, right? Okay, then from 69 kV to 115 kV, you can have this type of tower structure, right? Then from 115 kV to 345 kV, you can have this type of tower structures. Okay, so as you can see over here, this carries 2 circuits, right? One A, B, C. So that is one circuit, right? A, B, C. That's a second circuit. So this tower structure carries a double circuit, especially during some of the transmission lines when you want redundancy in the flow of power. Next is tower structures up to about 345 kV, right? You can have instead of this tower structure, you can have this other tower structure where basically you have one phase over here, A, B, C, right? So you have one circuit on this side, then you have another circuit, A, B, and C, right? Okay, so these monopole structures basically to support have the capability to support double circuits, right? Okay, then you can have this tower structure that can support voltages all the way up to 765 kV. So that is a extra high voltage, right? Okay, so as you can see over here, each suspended insulator, right, basically holds 4 conductors, right? You can see 1, 2, 3, 4 that are held together, bundled together. So this is phase A, phase B, phase C, right? Okay, so this is the type of suspended insulators that holds the conductors, the phase conductors. Okay, so now let's take a deep dive on the type of support insulators, right? So this is an example of a cross arm, right? So this cross arm is part of the tower structure, right? So right connected to the cross arm is that vertical insulator, suspended insulator, right? This suspended insulator can be in the form of a V shape. It can be in the form of vertical. It can also be in the form of a horizontal, right? Okay, so this is a typical of a vertical suspended insulator. Suspended insulator. You can also have a horizontal suspended insulator. Okay, so this insulator that can be made from polymer, it can also be made from a polymer, right, or composite insulation, or porcelain, or hardened glass, right, that are put together. So each disc has a voltage rating, typically about 11 kV, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 11 times 9, right? 99 kV, right? Okay, so this one probably about 69 kV transmission line, right? Okay. Next is another support vertical support insulator, right? Okay, so this one is utilizing porcelain, right? As you can see over here, this one is glass, right? Hardened glass. This one utilizes porcelain, right? You know, so porcelain is like a pottery material made from clay, right? Okay, so what you can see over here are corona rings, right? Right over here. And what is the function of this corona rings? Okay, so as you know, you have a high voltage that is connected here, right? You have a high voltage that is connected here, right? Okay, so this has been stacked, you know, so this one is like a double stack, right? Okay, so one stack, based on the voltage level, transmission line voltage level, right? Okay, so you have a basically high voltage here, and basically you have air insulation, right? Over here you have air that is acting as an insulating medium around this solid porcelain, right? Okay, so because the voltage is so high, right? There's something they call electric field stress, right? Which is based on the voltage over the distance, right? Over the distance right here where the conductor is connected. Okay. So the smaller the distance, the higher your electric field stress, right? And the goal is to reduce the electric field stress to a withstand capability, right? So that is why they put these corona rings, right? That basically increases the distance, right? Increases this D over here, so that the electric field decreases around these external porcelain insulators to prevent corona from occurring, which can damage the external porcelain insulator. Another support insulator, which is basically used in distribution level, right? Is a pin type insulator, right? Basically, that holds the conductor on top, and basically this pin type goes inside. Basically, if it is a pole mounted, wooden pole mounted, it goes in over here, and the insulator is bolted on top, and the conductor goes over here. So this is basically utilizing distribution type, tangent type of pole, and a tangent type of transmission line distribution system. Next is a close view of what a damper looks like, you know, and I explained what a damper weight is. Its goal is to basically add a weight to the phase conductors to damp out any vibration that can occur due to excessive wind velocity that basically can create galloping or wind clashing. Okay, so this one is a suspended vertical insulator. Basically, it provides a ground plane of the phase from the phase conductor to the cross arm conductor. So that as you know, the cross arm conductor is a ground plane, right? So the goal is basically to provide the mechanical support. It's doing two things. It's providing a ground plane, right? And secondly, it is providing the mechanical support to these phase conductors, right? To keep it in place, right? To prevent it from galloping or clashing into other phase conductors. So that is what these components are. Next is a deeper look into how this horizontal support insulators looks like. Okay, so as you can see, this is made of several discs, right? So think about it. Each disc can withstand 11 kV. So, if you count this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, right? So 11 times 27, right? And I remember they can also put a lot of these in parallel, right? To basically to support the required withstand voltage that they need. Next is the phase conductors, right? As you can see over here. So from one tower to the next tower is called what they call the span, right? Okay, so like I indicated, sometimes you can have about 2 conductors in phase or 4 conductors in phase, and you need a spacer that will hold these phase conductors in place. Okay, so as you can see it over here, right? Beautiful over here. This each phase consists of 4 conductors, right? Matter of fact, 6 conductors, right? 1, 2, 3, 4, 5, 6. Okay, so these are tied together with this spacer, right? So 6 conductors per phase, right? So phase A has 6 conductors that are bundled together. Phase B has 6 conductors that are bundled together. Phase C has 6 conductors that are bundled together. And I explained to you the purpose of putting that many conductors in phase is because of the high current, and the goal is to distribute, put this current phase conductors in parallel so that the current can be distributed, can be shared among these conductors, right? Okay, so over here is the corona ring, right? The goal is to protect this basically horizontal insulator, right? Because of the high voltage here, right? So this one is basically a jumper, right? Okay, so you have a tower structure here. I think that part is probably not part of this picture, right? Okay, so this is the phase conductor, right? So this one is a jumper that goes to the other end of the tower, right? To the other side of the transmission line. So you have a transmission line on this side, you have a transmission line on this side. You have a tower, right? And you have a jumper, right? Because this one is a ground plane, right? So for you to provide continuity from this line end of the transmission line to this line, and you need a jumper, right, to connect this from end to this end, right? So bundled conductor is this one, spacers is this one, and corona ring is this one. It's a horizontal suspended insulator, right? Okay, so like I told you that, as you can see over here, this is basically made in it's 3 of them in parallel, right? And they've been put together or stacking up all the way, and based on the transmission voltage level. So if you have a 765 kV line to line, what they do is they calculate the line to ground voltage, right? That is 765 divided by √3, right? So that will give you your line to ground voltage, right? Then if each disc can withstand 11 kV, right? So to calculate the number of discs, you divide this by 11 kV, and that will give you your total number of discs that you require. Next is is another transmission line. Okay, so what they call a span, right? A span from one tower to another tower. It's this distance, right? That is what they call a span. And as you can see, this is a whole tower structure and its members, right? Okay, and this is a cross arm, and a cross arm, right? Okay, so these cross arms are the ones that are holding the phase conductors, right? And this is a vertical suspended insulator, right? That is holding the phase conductors are being held over here, right? And as you can see here, this is a jumper, right? And the phase conductors are being held over here, and this one has about 6 conductors that are being held in a bundle together in phase. Okay, so it also has a shield wire, as you can see over here. It's a shield wire over here. Okay, so this is a deeper look into the corona ring, right? And I explained what the corona ring, right? Its goal is to provide that grading voltage to reduce the electric field stress that can be experienced at this connection point, right? So basically, and to prevent breakdown of the insulator, right? Okay, so if this one insulator is a polymer or porcelain, right? And now you have a live connection point here, there'll be high electric field, and the goal is to put this corona ring over here so that you can have V over D, and that your D will be greater, and your electric field will be much lower. Okay, so next is different tower structures, right? Okay, so as you can see over here, this is a vertical suspended insulator, right? Okay, so you have the vertical insulation that is basically suspended, right? And basically holding the phase conductors, right? Okay, so this one is more of a tension, right? So tension is basically when you are trying to change direction. This one is usually utilized for straight, transmission line that basically goes on a flat line, right, all the way, without any impediments, right? Okay, straight. So this is the type of tower structure that is utilized. Okay, but if you want to change the direction of the transmission line, let's say have it basically over, a heated place, and then basically that is when you utilize this type of towers that can basically allow you to change the direction, let's say from an angle, onto the next direction. Right. Next is another tower structure, basically suspended insulator, and you have the horizontal type and the vertical suspended insulators, and you have the ground wire over here, right? So this one is also a suspension tower, right? Okay, so they have suspension insulators over here, right? So the suspension insulators, right, you can have different types, based on the voltage level. Okay, so this one is for 500 kV, and this one is for 765 kV, and this one is for up to 230 kV, right? Okay, and this one is a tangent or tension type of tower. With that comes to the end of my presentation, and thank you so much for your listening ears. And don't forget to go to my YouTube channel, and if you like this presentation, don't forget to select the like button and subscribe to my channel, and look forward to more interesting presentations. With that, I'll say thank you so much.